how did you get on with assignment 6? If you've followed everything so far and managed to do fairly well on all 6 assignments, you should have a good idea of the kind of linguistic precision required in mathematics. Now we can start to put that precision to use in proving mathematical statements. In the natural sciences, truth is established by empirical means, involving observation, measurement, and, the gold standard, experiment. In mathematics, truth is determined by constructing a proof, a logically sound argument that establishes the truth of the statement. The use of the word argument here is, of course, not the more common everyday use to mean a disagreement between two people. But there is a connection in that a good proof will preemptively counter, explicitly or implicitly, all the objections, the counter-arguments, that a reader might put forward. When professional mathematicians read a proof, they generally do so in a manner reminiscent of a lawyer cross-examining a witness, constantly probing and looking for flaws. Learning how to prove things forms a major part of college mathematics. It's not something that can be mastered in a few weeks. It takes years. What can be achieved in a short period, and what I'm going to try to help you do here, is gain some understanding of what it means to prove a mathematical statement and why mathematicians make such a big deal about proofs. First, what is a proof and why do we use them? I'll answer the second question first, since their purpose dictates what they are. Proofs are constructed for two main purposes: to establish truth and to communicate to others. Constructing or reading a proof is how we convince ourselves that some statement is true. I might have an intuition that some mathematical statement is true, but until I've proved it or read a proof that convinces me, I can't be sure. But I may also have to convince someone else, and that's the second purpose of a proof. For both purposes, a proof of a statement must explain why that statement is true. In the first case, convincing myself, it's generally enough that my argument is logically sound and I can follow it later. In the second case, where I have to convince someone else, more is required. The proof must also provide that explanation in a manner the recipient can understand. Proofs written to convince others have to succeed communicatively as well as be logically sound. There's actually not as much of a distinction here as my words might imply. For complicated proofs, the requirement that a mathematician can follow his or her own proof a few days, weeks, months, or even years later can also be significant. So even proofs written purely for personal use need to succeed communicatively. The requirement that proofs must communicate explanations to intended readers can set a high bar. Some proofs are so deep and complex that only a few experts in the field can understand them. For example, for many centuries, most mathematicians believed, or at least held a strong suspicion, that for exponents n greater than or equal to 3, the equation x to the n plus y to the n equals z to the n has no positive whole number solutions for x, y, and z. That was conjectured by the French mathematician Pierre de Fermat in the 17th century, but it wasn't finally proved until 1994, when the British mathematician Andrew Wiles constructed a long and extremely deep proof. Over the centuries, it became popularly known as Fermat's last theorem, since it was the last of several mathematical statements Fermat announced that remained to be proved. Most mathematicians, myself included, lack the detailed domain knowledge to follow Wiles' proof ourselves. But it did convince the experts in the field by the way is analytic number theory, and as a result, Fermat's ancient conjecture is now regarded as a theorem. Fermat's last theorem is an unusual example, however. Most proofs in mathematics can be read and understood by all professional mathematicians, though it can take days, weeks, or even months to understand some proofs sufficiently to be convinced by them. I've chosen the examples in this course to be understood by a typical student in a few minutes, or possibly an hour or so. Examples given to college mathematics majors can usually be understood with at most a few hours' effort. Proving a mathematical statement is much more than gathering evidence in its favour. To give one famous example, in the mid-18th century, the great Swiss mathematician Leonhard Euler said he believed that every number beyond 2 can be expressed as a sum of 2 primes. This property of even numbers had been suggested to him by Christian Goldbach and became known as the Goldbach conjecture. It's possible to run computer programs to check the statement for many specific even numbers, and to date, 2012, it's been verified for all numbers up to and beyond 1.6 quintillion. Most mathematicians believe it to be true, but it's not yet been proved. All it would take to disprove the conjecture would be to find a single even number n for which it could be shown that no 2 primes sum to n. Incidentally, mathematicians don't regard the Goldbach conjecture as important. It has no known applications or even any significant consequences within mathematics. It's become famous solely because it's easy to understand, was endorsed by Euler, and has resisted all attempts at solution for over 250 years. Whatever you may have been told at school, there's no particular format that an argument has to have in order to count as a proof. The one absolute requirement is that it is a logically sound piece of reasoning that establishes the truth of some statement. An important secondary requirement is that it's expressed sufficiently well that an intended reader can, perhaps with some effort, follow the reasoning. In the case of professional mathematicians, the intended reader is usually another professional with expertise in the same area of mathematics. Proofs written for students or laypersons generally have to supply more explanations. This means that in order to construct a proof, you have to be able to determine what constitutes a logically sound argument that convinces not just yourself, but also an intended reader. Doing that's not something you can reduce to a list of rules. Constructing mathematical proofs is one of the most creative acts of the human mind, and relatively few are capable of true original proofs. But with some effort, any reasonably intelligent person can master the basics, and that's my goal here. Euclid's proof that there are infinitely many primes, which I gave in the first lecture, is a good example of a proof that requires an unusual insight. Let's look at it again.
Here's what we did. The idea is to show that if we list the primes in increasing order, then the list can be continued forever. So we imagine that we've listed the primes, P1 is 2, P2 is 3, P3 is 5, etc., all the way up to some stage Pn, and we show that we can always add another prime to the list. And to do that, we look at this number n, which we obtain by multiplying together all the primes in the list so far, and then adding 1. Now this number, n, consists of the product of all those numbers p1 through pn plus 1, so it's certainly bigger than all of those numbers. So it's bigger, so n is bigger than all the primes in the list. Well, if n is prime, then we know that there's a prime bigger than Pn, namely n, in which case we can continue the list. Probably not by adding n itself. N, because it's the product of all these plus 1, is going to be a lot bigger than Pn, so n is almost certainly not the next prime. But that doesn't matter. If n is prime, it shows there is a prime bigger than the one at the end of the list, and that means we can continue the list. The alternative is that n is not prime, in which case there's a prime q less than n that divides it. But none of the primes in the list can divide n. since if you divide n by any of those primes, you're left with that remainder 1. If you try to divide p1 or p2 or any of these primes into this number n, it gets swallowed up by this part, and then there's a remainder of 1. Okay? So q has to be bigger than pn. Those are the first n primes, so if q is not equal to one of those, it must be later on in the list. In which case, we've shown again that there's a prime bigger than pn, and the list can be continued. Again, this particular q that divides n is not necessarily the next prime, but as before, that doesn't matter. Showing that there is another prime is all you need to do, because then you can take the next prime, whatever it is, and add it to the list. Either way, either if n is prime, or if n is not prime, either way, there's another prime to add to the list. It follows that there are infinitely many primes. And the theorem's proved. There are two creative ideas in this proof. The first one is here, to show that if we list the primes in increasing order as p1, p2, etc., then the list can be continued forever. So the first creative idea is to think about listing the primes and showing that the list can always be continued. The second creative idea was this one. Defining this number n in such a way that it guarantees that we can always find another prime. I would say that this idea is one that most mathematicians would come up with sooner or later. It's a fairly obvious one. This one is genius. Okay, this is true genius. Let me give you another example. And this time I'm going to prove that result I promised earlier, that the square root of 2 is irrational. And I'm going to write it the way mathematicians typically do when they write up results for publication in professional journals or in books. Namely, we call it out by calling it a theorem. So in mathematics, a result that's sufficiently significant or important that it's worth mentioning as such is called a theorem. In this context, let me mention there's another word we often use called lemma. And a lemma is a result which is worth calling out for some reason, but doesn't quite merit the status of being called a theorem. It's actually, if you like, a little theorem. Okay, the next thing a mathematician typically does is indicate that we're going to begin the proof. Okay? So this is just part of the way mathematicians lay things out. We specify the theorem, and then we say we're going to give the proof. You don't have to do it this way, it's just a convention. The essence of being a proof is what comes next. Proofs are about their logical structure, not the way we write them down. I'm going to begin by assuming, on the contrary, that the square root of 2 were rational. Now, if you've never seen the proof that the square root of 2 is irrational before, this first step is going to seem pretty mysterious. Why do I begin by assuming the opposite of what I'm trying to prove? Well, by the time I get down here, you'll see why. The reason this is a great example is in about 6 or 7 lines, I can make it clear why I'm doing something right in the first step. Okay. Well, in that case, if square root of 2 were rational, then there are natural numbers pq with no common factors, such that the square root of 2 is p over q. Remember, a rational number is one that can be expressed as the quotient of 2 integers. In the case of a positive number, it would be 2 natural numbers. And we can always pick those natural numbers, or those integers, to have no common factors. In other words, when we write a rational number as a quotient, we can always cancel out any common factors and express it as a quotient where the 2 numbers themselves have no common factors. Again, it might seem a little bit mysterious why I'm being particular about cancelling out common factors, but as with the first step, by the time I get down here, it'll be clear why I'm doing this. Well, squaring that equation gives me 2 equals p squared over q squared. Rearranging, I get 2q squared equals p squared. I multiply both sides by q squared, that gives me a 2q squared on the left, and then when I multiply the right by q squared, it cancels that q squared and I'm left with a p squared. So p squared is even. It's equal to twice something. Hence, p is even. Why? Because the square of an even number is an even number, the square of an odd number is an odd number, so the only way I could get the square of a number p to be even is if the number p itself is even. Even squared is even, odd squared is odd. So p is 2r for some r. I'm now going to take this equation, p equals 2r, and use it to substitute back in this equation. So I take this equation, I've got 2q squared equals p squared, and p equals 2r, so I've got 2q squared equals 2r all squared, which is 4r squared. Well, we'll forget the middle term now. I've got 2q squared equals 4r squared. I can cancel the 2. Well, if q squared is 2r squared, then q squared is even. But exactly as happened before with p squared, if q squared is even, then q is even. Aha! You see what's happened? I've deduced here that p is even. I've deduced here that q is even. So p and q are both even. But they can't be, because we assumed p and q had no common factors. If they're both even, then they have 2 as a common factor. But this is impossible, since p and q have no common factors. Well, the logical reasoning here, the algebra, the arithmetic, is all sound. That's absolutely everything's perfectly sound. How can we have arrived at an impossible conclusion by a piece of sound reasoning? Well, the only thing that can possibly have gone wrong is we began by making a false assumption. Remember, we began with an assumption. The only way we can have reached a false conclusion by a valid argument, and this is valid. If you don't believe me, go and check it for yourself. There's not many steps. See if there's anything wrong in any of these steps. There isn't. If we reach a false conclusion by a logical argument, then we must have started with a false assumption. Hence, the original assumption that the square root of 2 were rational must be false. Hence, square root of 2 must be irrational. And when I was at school, teachers used to insist that we write QED at the end of a proof, Quod Demonstrandum, which is Latin. It is actually not a bad idea to indicate when a proof ends, and mathematicians have different ways of doing it. Sometimes they write a little box at the end. How you express it, I mean, how you lay it out on the page is not that critical. I mean, the idea is to lay it out in a way that can be followed. What makes a proof isn't the fact that you call it a proof, it isn't the fact that you end in a QED, it's the logical flow of the steps. It has to be logically precise, and you have to be able to follow it. Well, there's the proof. The reason this is a good example to give is it's short, it's concise, and all of the steps are simple arithmetical steps. It's very easy to follow every step, and yet when you followed this small number of simple steps, you've proved a significant result. In fact, this result, when it was first discovered by one of the Pythagoreans in ancient Greece, was dramatic. It changed the course of Greek mathematics, because until then they felt that quotients of integers were sufficient to measure any length. But square root of 2 is the length of the diagonal of a right-angled triangle whose sides measure 1. And when this result was proved by one of the Pythagorean mathematicians, it showed that quotients of integers were not sufficient to measure all lengths in geometric figures. And that changed the course of Greek mathematics and subsequently the rest of mathematics. It was extremely dramatic. Incidentally, there's a story you'll read about in books and on websites that say that this was discovered by a young mathematician, and that the Greek mathematicians, the Pythagoreans, were so annoyed and so scared that this would kill their career and their profession that they threw him overboard. There's absolutely no evidence whatsoever that that was the case. It's a great story, but like many stories, it's probably not true. Okay, but in any case, we've now shown that the square root of 2 is irrational, and there we go. I mean, this is really a remarkable result, very short, very elegant. Incidentally, when mathematicians talk about aesthetics, when they talk about an elegant proof or a beautiful proof, this is the kind of thing they have in mind. Not that it looks beautiful the way it's written out. In fact, I've just worked through it and it doesn't look particularly beautiful to look at, but the logical structure is beautiful. Every step counts, the result is established, and every step can be understood fairly straightforwardly. The complexity doesn't come because there's deep results involved, deep facts, deep concepts. The proof works because of the structure, the logical structure. Okay, so now you know why root 2 is irrational. Let me say a little more about that proof. It's an example of what mathematicians call proof by contradiction. And proof by contradiction is a general method that works as follows. You want to prove some statement phi. You start by assuming not phi. You reason until you reach a conclusion that's false, often by deducing both psi and not psi for some statement psi. For example, in the proof that the square root of 2 was irrational, we proved that P and Q have no common factors, and yet we knew that P and Q were both even. So we have a statement and its negation. Or not strictly speaking it's negation, but close enough for these purposes. This is not an exact rendering of psi and not psi. But the point is we've deduced two contradictory things. It cannot be the case that they have no common factors and that they're both even. But a true assumption cannot lead to a false conclusion. Hence the assumption not phi must be false. Remember, we began by assuming not phi. We reach a false conclusion, a contradiction. A true assumption can't lead to a false conclusion, so the assumption must be false. In other words, phi must be true. If not phi is false, then phi is true. Well, we begin by wanting to prove some statement phi, and we're going to end up with phi. And in the middle, we reason by assuming the contrary. So here's the contradiction proof going on in here. There's phi, there's phi. In here we're reasoning with not phi. We start by assuming not phi, and we reach a conclusion, a false conclusion, and conclude that that's false. Let me say a little bit more about this. We can look at proof by contradiction in terms of truth tables. What can we conclude from a proof of theta yields psi where psi is false? In the case of the proof of root 2 being irrational, the theta was the statement square root of 2 is rational, and the psi was the false statement that we never actually wrote out in full, that p and q are both even and have no common factors, which is false, because there's no such, there are no pairs of integers which are both even and have no common factors. So in terms of proofs by contradiction, the theta is the assumption you make at the start of the proof, and the psi is the false conclusion you reach at the end. So I'm going to use truth tables to understand how it is that starting with an assumption and reaching a false conclusion leads to concluding that the assumption was false. And since the assumption was counter or contrary to the thing we're trying to prove, that would amount to proving the theorem. Okay. So I'm going to write down the truth table for theta yields psi, or theta conditional psi. Write the truth values down: t, 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 f, f, t, f, f. And we know what the table looks like here. It's t, f, t, t. Well, if we've carried out a proof of this, that means this thing is true. Right? So we can forget that line. We're only interested in what happens when this thing is true. So we've carried out a proof that this implication, this conditional, is true. So it's one of these three. In this case, however, the psi is false. Where's the psi false? Well, here psi is true, here psi is true, here psi is false. So this is the only line in the truth table which fits this. We have this being true, which means it's one of these three, and we have psi being false. That's the only possibility. In other words, theta is false. So when in a proof by contradiction you make an assumption, a counter assumption, an assumption counter to what you're trying to prove, and you carry out some reasoning to deduce a false conclusion, a contradictory conclusion, or a contradiction, so you've established in your argument that this thing is true. This says that the argument is valid. Then the conclusion, from having reached a false conclusion, the big conclusion, the global conclusion, is that your original assumption is false. Okay, it's a little difficult to explain this in words because we have to keep talking about truth and falsity and assumptions and conclusions, and there are assumptions and sub-assumptions and so forth. But if you go through the original proof that square root of 2 is irrational once more, and then think about it in terms of what I just said a moment ago about proof by contradiction in general, and then think about it in terms of this truth table analysis, and hopefully you should be able to understand why proofs by contradiction work. It's a very clever idea, and they're used a lot in mathematics. And I've just noticed I've misspelt truth table, so let me put the L in there. Okay, there we go.
That was a fairly lengthy discussion of such a short argument. But I know from many years of experience that beginners find the root 2 proof hard to really understand. You may think you understand it, but do you really? Let's see if you can produce a similar one. Try to prove that the square root of 3 is irrational. You should definitely try to do this exercise, but be prepared to spend some time at it. Remember, this is not a book about solving problems. The goal is to learn to think mathematically. And just like learning to ride a bike, to ski, or to drive a car, the only way to do that is to keep trying for yourself. Looking up the answer or being shown it by somebody else just doesn't help. It really doesn't. Look it up now and you'll pay heavily later. The value comes from spending time trying to solve it for yourself. Go on, give it a try. I'll say it again. This course is about the process of thinking, not about getting results. You can use the thinking abilities you develop in a course like this to get results in other courses and in other situations in your life. It doesn't matter if you don't get the root 3 proof. You'll have benefited from trying. Proofs by contradiction, which we use in the root 2 theorem, are a common approach because they have a clear starting point. To obtain a direct proof of some statement phi, you have to generate an argument that culminates in phi. But where do you start? The only way to proceed is to try to argue successively backwards to see what chain of steps ends with phi. There are many possible starting points, but just one goal. And you have to end up at that goal. That can be difficult. But with proof by contradiction, there is a clear starting point, and the proof is complete once you have deduced a contradiction, any contradiction. With such a wide target area, that's often a much easier task. The proof by contradiction approach is particularly suited to establishing that a certain object doesn't exist. For example, that a particular kind of equation does not have a solution. You begin by assuming that such an object does exist, and then you use that assumed object to deduce a false consequence or a pair of contradictory statements. The irrationality of the square root of 2 is a good example, since that states the non-existence of two numbers p and q whose ratio is equal to root 2. Even though there is no cookie-cutter template approach to constructing proofs, there are some guidelines. We just met too. Proof by contradiction is often a good approach when there's no obvious place to start. And proof by contradiction is a useful method to prove non-existence statements. Of course, you still have to construct a proof. You've simply replaced a narrow goalpost with an unclear starting point by a much wider one with a known starting point. But like Robert Frost's fork in the trail, that choice can make all the difference. There are a number of other guidelines. I'll tell you some, but do bear in mind that these are not templates. As long as you continue to look for templates to construct proofs, you're going to encounter significant difficulties. You have to start each new problem by analysing the statement that you want to prove. What exactly does it say? What kind of argument might establish that claim? Let's look at another guideline. How might you go about proving a conditional statement, one of the form A implies B?
We want to prove a conditional phi yields psi. Well, we know this is true if phi is false, so we can assume phi is true. Why do we know it's true if phi is false? Well, that was part of the definition of the conditional that we developed using truth tables. So to prove it, we assume phi and deduce psi. This, of course, confirms the point I made earlier, that despite its strange definition, its counterintuitive definition perhaps, the conditional really does capture genuine implication, because in all actual practical examples, when you try to establish a conditional, what you do is you assume phi and you deduce psi. And this is genuine implication. This says that psi is following from phi. For example, let x and y be variables for real numbers and prove the following. If x and y are rational, then x plus y is rational. Okay, this is not a surprising result. This is nothing deep. I'm focusing not on the result, but on the method I use to prove it. And so I've deliberately chosen an example that's extremely simple so that we can look at the process of reasoning that's involved in proving a conditional. So step 1, assume x and y are rational. In that case, there are integers p, q, n and m such that x is p divided by m and y is q divided by n. Where in that case, x plus y is p divided by m plus q divided by n, which equals pn plus qm divided by mn. Hence x plus y is rational. Okay, as I mentioned a moment ago, there's nothing surprising here. It's almost not a proof at all. It's just really adding two things together. But it actually is a proof because it has the right structure of a proof. Here's what we did. We began by assuming x and y are rational. We concluded that the sum is rational. And in the middle, there was an argument to demonstrate that fact. The argument was actually fairly typical in what we first did was take the assumption and then unpack the assumption in terms of some useful information. And once we'd done that, we reasoned with that information to get a conclusion that in fact was the thing we were aiming for. So we write down the assumption, we carry out some reasoning, and we reach the conclusion. All three steps are important. Declare the assumption, carry out the reasoning in a clear, understandable fashion, and then state the conclusion when you've reached it. Remember that proofs have two purposes. One is to convince yourself, and two is to convince other people. And you may know what you're doing if you don't mention what your assumption is or what your conclusion is, although I'll guarantee from experience that a week from now you'll forget exactly what you were doing. So it really is good, even for your own purposes, to write down what your assumptions are. But certainly from a communicative angle, it's important to begin by stating the assumption, then to lay out the reasoning in a simple, understandable fashion, and then to state the conclusion that you've reached. Okay, well that's the most basic method of proving a conditional. Let me give you a quiz. Let R and S be irrational numbers. Say which of the following are necessarily irrational. And let me stress that word, necessarily. Number 1, R plus 3. Number 2, 5 times R. Number 3, R plus S. Number 4, R times S. And number 5, square root of R. Now this is a quiz format where I'm just asking you to select the ones that you think are necessarily irrational. But unlike most of the quizzes, where I expect you to be able to answer very quickly, I'd like you to think a little bit before you answer each of these, because the focus isn't really on getting the answer right. I mean, obviously I want you to get the answer right. I'm sure you do too. But that's not the focus. The focus is on the reasoning that you need to carry out in order to get those answers. In each case, you're probably going to have to carry out 1 or 2 lines of simple reasoning in order to answer the question. That's the focus of this particular quiz. In fact, in the assignment that's coming up in assignment 7, I'm going to ask you to write out proofs of each of the 5 answers. So let me stress that the focus is on the logical reasoning. Okay, see how you do. Well, the ones that are necessarily irrational are 1, 2, and 5. In each case, you use the fact that a rational number is one that can be expressed as a quotient of 2 integers, and an irrational number is one that cannot be so expressed. And then you carry out a couple of lines of reasoning to show that
r plus 3 has to be irrational. If r plus 3 was rational, then r would be rational. Likewise, you would carry out a couple of lines of reasoning to show that if 5r was rational and could be expressed as a quotient of two integers, then so could r. And similarly, you carry out a similar argument for the square root of r. The two that are not necessarily irrational are 3 and 4. In order to show that r plus s is not necessarily irrational, what you would need to do is find examples of irrationals r and s for which the sum is rational. Well, how about taking r is the square root of 2 and s equal to, let's say, 10 minus the square root of 2. R plus s is equal to 10, which of course is rational. It's an integer. We know that the square root of 2 is irrational, and a very simple argument shows that 10 minus the square root of 2 must be irrational. In fact, the argument you use to show that this number is irrational is a combination of the two arguments you used in parts 1 and 2. Okay, so r and s are irrational, but their sum is rational. In the case of this guy, we could take r equals square root of 2 and s equals square root of 2. R and s are both irrational, and yet r times s is 2, which is rational. Okay, how did you do? Remember that in assignment 7 I'm going to ask you to give proofs of each of the 5 answers. Well, conditionals involving quantifiers are sometimes best handled by proving the contrapositive. What's the contrapositive? Well, we met that in assignment 4. So to prove a conditional phi yields psi, what you can do is prove not psi yields not phi. That's the contrapositive of phi yields psi. You reverse the phi and the psi and you put negations in front of them. And in assignment 4, if you look back, we proved that those two are equivalent. We proved that using truth tables. So let's look at an example of how this might work. And the example I'll take is this one. I want to prove that if the sine of an angle theta is not equal to 0, then for all n in the natural numbers, theta is not equal to n pi. Okay, there's a conditional, and I'm in the middle of some argument, we'll imagine, and I want to prove that if the sine of theta is not 0, then theta is not a whole number multiple of pi. Well, the statement's equivalent to not the case that for all n in n, theta not equal to n pi, implies not that sine theta is not 0. Well, there's lots of nots in here, so let's clear them all out and put this into a positive form. So, in positive form, this is not for all n in n. We're going to get there exists n in n, and the not is going to move inside, and it's going to negate this not. It's going to wipe that one out, and then I'm going to have theta equals n pi. Yields not that sine theta is not 0 means that sine theta is 0. So this is the contrapositive of this, and that's the thing we're trying to prove. Well, we know this. We know that whenever you've got a whole number multiple of pi, its sign is 0. So this proves the desired result. Obviously, this is a highly contrived, manufactured example. Again, the focus is not what I'm actually proving, it's the method I'm proving. I'm picking simple examples
so that we don't have to worry about the mathematical content. We can just look at the logical reasoning. And in this case, we start out, we want to prove something, we replace it by the contrapositive, and then we prove the contrapositive. In this case, the proof of the contrapositive, we just pull on well-known knowledge about the sine function, that the sine crosses the x-axis whenever you're at a whole multiple of pi. Okay, let me tell you about one more thing involving proofs of conditionals. To prove a biconditional, phi equivalent to psi, we generally construct two proofs, one of phi yields psi, the other of psi yields phi. And since the biconditional is just a conjunction of the two conditionals, that clearly amounts to a proof of the biconditional. Occasionally it's easier to prove the two conditionals phi yields psi and not phi yields not psi. And I'm going to leave you to find out why this is enough. Why does this work? If you look back at the assignments, you should find a clue as to why it's enough to prove these two in order to prove the biconditional. Okay, now I'd like you to complete assignment 7. As usual, completing an assignment means at least you should attempt all of the questions. You may not be able to get them all out, at least not at first. But remember, the benefit from working on the assignments in this course is actually trying them. Whether you get them out or not is not that important. Remember my favourite example of learning to ride a bike? The fact that you don't succeed in riding a bike for many days or weeks when you're learning doesn't mean you're not making progress. The same with learning to swim. You actually get the benefit during the process when you're trying and failing, and then suddenly you find you can either ride the bike or you can swim. And it's the same with this kind of material in this course. Okay, good luck on assignment 7.